Hello, in this video we're in the multiple linear regression setting and we're going to look at indicator variables, sometimes called dummy variables. So here's our model. Y is equal to x beta plus epsilon. X is a design matrix. Beta is a vector of k plus 1 by 1. And really, to illustrate indicator variables, I'm going to go through two examples. And these examples are actually from my class notes many moons ago. So let's let Y be the sales at a restaurant, how much money they make. X1 is going to be the number of households in the restaurant's area. And let's suppose that some restaurants are in a shopping mall and then some are on the street, And how would we model those two, these three things? So X1 is number of households, and then we have a variable maybe called, location or something like that. So here's some possible settings. That the street and mall restaurants roughly have the same slope and the same intercept, or they could have the same slope but different intercepts. They could have different slopes and different intercepts. And so we want to build models for each of these three scenarios. So model A, we're going to let Y equal to beta 0 plus beta 1 x1 plus epsilon, our error. So here we're not factoring in location, whether the restaurant's in a mall or a street. We're just putting them all together. And so the expected value of this, these are constants, that's 0, it's this, so it's that line. Now for the next two scenarios, so for models B and C, we're going to define this dummy variable or indicator variable, same thing, where it's a 1 if the restaurant is a mall restaurant and 0 if the restaurant is on the street. Then this indicator variable will help us model these two situations. So for model B, we add this indicator variable into our model. And so now let's look at the different cases. So if it's a mall restaurant, the observation is a mall restaurant, x2 is 1, right? And so the model becomes this, the expected value of Y. So these are constants. X2 is 1, so we're just left with beta. And then we can kind of regroup it this way. So we have the slope and we have the intercept. Now, if we're talking about a street restaurant, X2 is 0. So now we plug X2 0 in the model. So this goes away. And the expected value then becomes this. Now, note that they have the same slope, beta 1, but they have different intercepts. This is the intercept for the mall restaurants, and this is the intercept for the street restaurant. So this is the model that we'd use for situation 2. Now situation 3, we have to add in what's called second order terms. So here's our model. So beta 0, beta 1 x1, we have beta 2 x2, and then we have this second order term. It's the product of x1 and x2. But remember, x2 is either 1 or 0, depending upon whether it's a mall restaurant or a street restaurant. So now let's look at the mall restaurant. So x2 is 1. So we put a 1 here and we put a 1 here. And then if we look at the expected value, we get this. Now let's regroup terms and we get this. So this is the intercept and this is the slope of the line for mall restaurants. Now street restaurants, x2 is 0, so 0, so this goes away, that's 0, so it goes away. The expected value is just this. So the notes, we have different intercepts, right, there and there, and we have different slopes, right? This is the slope of street restaurants, this is the slope of mall restaurants. Now these models are nested. So if we're in model C, which is this one here, and if beta 3 is 0, then it reduces to model B. If beta 2 and beta 3 are both 0, then it reduces to model A. If we start out with model B and we test it, and if beta 2 is 0, then it reduces to model A. Now let's look at a second example, but we're going to build upon the first example. So Y is going to be the sales of the restaurant. X1 is going to be how many households are in the restaurant's area, but for location, we're going to assume that we have street restaurants, we have restaurants in a shopping mall, and we have restaurants near an interstate highway. So note that location has 3 levels, right? Street, shopping mall, and interstate. So this is going to require 2 dummy variables to code location. So however many levels there are, you use 1 less dummy variable to code it, okay? So to code these 3 locations, we use 2 dummy variables. So X2 is a 1 if it's a mall restaurant and 0 otherwise. X3 is a 1 if it's a street restaurant and 0 otherwise. And these 2 is all we need to code these 3 variables. So let's look at the same slopes but different intercepts model. And that's where we just have first order terms. So Y is equal to beta 0, beta 1 x1, beta 2 x2, beta 3 x3, and the intercept. So there's no second order terms in here. So when we look at the expected value of this equation, so for mall, x2 is 1, x3 is 0. So this is 0, this is 1. So its expected value is this. So it has this as an intercept and beta 1 is the slope. For street restaurants, x2 is 0 and x3 is 1. So plug those in and the expected value is this. So the same slope but different intercepts. Now if we're looking at an interstate restaurant, x2 is equal to 0, x3 is equal to 0. So you plug those in and then what's left is this model. So that all 3 have the same slope but they have different intercepts. So that's how you would code that. And we'll just do one more little scenario for this situation. Let's assume they have different slopes and different intercepts. Now different intercepts means these first order terms, the dummy variables here are first order terms. Now to have different slopes for the different situations, we need to create these second order terms, sometimes called an interaction term. And now let's look at that. So if we're in the mall, x2 is 1, x3 is 0. Its expected value is this. So this is the slope, this is the intercept. If we're dealing with the street restaurant, x2 is 0, x3 is 1. Its expected value is this. Different slopes, different intercepts. Interstate, x2 and x3 are 0, so plug in 0 for all these. And then we're left with this expected value, this model. So notice they have different slopes, different intercepts. So this is the model that would fit that scenario. But let's look at the design matrix for this model, okay? And this is it. So here the first column, of course, is all 1s corresponding with beta 1. X1, or beta 1, deals with the number of households in a restaurant's location. So it's this. Now beta 2 is the indicator variable for malls, or the dummy variable for mall, and it's a 1 if it's a mall, and it's 0 otherwise. Now beta 3 deals with the x3 variable, and it's an indicator variable for streets. So 0, 1s when we're dealing with the street restaurant, and then 0 for all the others. Now these last terms, I'm going to flash up here. And so this is interaction term. So if it's a mall restaurant, this is a 1, and then that's the variable. If it's a street restaurant, it's a 0, so that goes away. If it's an interstate restaurant, that's a 0 and goes away. So the design matrix is just this variable x1 is copied right here, and then these are zeros. And for beta 5, it's the same way. So these are 0, and this is a the x1 variable is just copied over here. And so this is the design matrix for this. Now, some notation. Here we used xij in these here, and it's common to let I be the sample size within each group. So I is the first one, so we go from 1 to N1, 1 to N2, 1 to N3, and then J is the group. So we go 1, and then these are all 2s, and these are all 3s, and that's a way to distinguish the different variables. Now here, the total sample size is N3, N2 plus N1, right? And that's N, the total sample size. And last, all the previously discussed tests can be used in this model, for this model. So the global F test, the test, the overall model usefulness, T test when we're looking at the test for a single beta parameter, the partial F test if we want to test one or more beta parameters, the general linear hypothesis, and I have videos on all of these different tests back in the playlist, the generalized linear models for regression playlist. And note 2, and the last one, this is really the basic idea of Ancova, which is analysis of covariance, where you start introducing categorical variables and continuous variables into a linear models. And we'll go into much more detail when I start the design of experiments part of this playlist. Well, that's all I have for today. Hopefully you enjoyed that. I sure did. Please like the video and subscribe so you don't miss the next one. Thanks. Bye.